Yeah.
Okay, so we succeed in this. So good morning, everyone. I am Emanuele in the board of the Italian Young Professional Network of the International Association of Hydro-Environmental Research. This is our second webinar. Every 2 weeks, we try to propose a webinar. The previous webinar, I talk about hydropower, while in this webinar, we will have Simone Pagliara, who will, Simone is a civil engineer specialized in hydraulic engineering and hydrology, and he will talk about high energy air water flow at hydraulic structures. Simone has a background with a bachelor degree in civil engineering at the University of Pisa, and then a master's degree in civil engineering at the University of Bologna, and then also in hydrology at the Imperial College of London. He's currently pursuing his PhD degree in ETH Zurich with an experimental research project concerning the safe design of dams, bottom outlet for high velocity air water flow. So thank you, Simone, for your availability, and you can start.
Thanks, Emanuele, for the presentation. So, can you see the screen?
Yes. Okay.
Okay, so sorry for the delay. We had an unexpected truck burning outside my office. Now we are fine. So today I would like to talk about high energy air water flows at hydraulic structure, and also to give you a brief overview of my PhD project, what I'm working about at the moment. So just to give a bit of context, we are talking about reservoir dams, which play a crucial role in our economy and society for many different reasons, because they are used for hydropower energy production, for climate change mitigation, for flood protection, but also for agriculture and drinking water supply. And here you can find 2 examples, so Zone Dam in Switzerland and Hoover Dam in the US. And such dams, they feature large outlet works, which are used to ensure a safe conveyance of floods. 2 kind of such outlet structures are spillways that you can see in the sketch here, and bottom outlets. So for a typical dam, where this is the retaining structure, bottom outlets are located at the very bottom of the retaining structure. And so let's say that the head, the water head here is very high, and we have a pressurized flow. We have a gate chamber with a sluice gate, and here we have the transition from pressurized flow to free surface flow. And because of that, we need to provide some air to our flow to dissipate energy and to avoid safety issues. And so usually air vents are located right downstream of the gate chamber. And here on the right, you can see some picture of middle outlets in China, spillways in Turkey, and a low-level outlet in Austria. As I said before, low-level outlets are characterized by high velocities and turbulence levels due to the high head that usually have at their inlet, and these lead to air entrainment and transport, and also subatmospheric pressures may develop at the structure invert. And these subatmospheric pressures may trigger some serious issues, such as gate vibration, cavitation, and slug flow. And I would like to concentrate on cavitation during this presentation. So here you have 2 examples of cavitation damages. So this is the very famous damage at Oroville Dam Spillway in the US, which was a really serious issue concerning cavitation. And here you can see the cavitation damage. And this regards Glen Canyon Dam in the US, and in the middle outlet tunnel, you can see 11 meters of scour due to cavitation issues. And all of these problems can be mitigated with sufficient aeration via an air vent. So that's a good thing. So looking to low-level outlets, we said that they are safety structures. So the main purpose is to have a fast drawdown of the reservoir in case of emergency or maintenance. But they're also used for sediment flushing and also to release excess flow or environmental flow during flood events. And because of their importance, there are some strict requirements that need to be fulfilled, and they need to have excellent performances under all the hydraulic conditions. But also it should be easy to access them for maintenance, and they have to last long. So longevity is another requirement. And the main challenges are, as I introduced before, that we are facing climate change. We are facing increasing demands in the near future. So higher flood peaks, higher reservoir sedimentation, dam heightening to tackle these problems. And so low-level outlets will be more and more stressed in the future. And the bad thing is that most of them have been built decades and decades ago, so they need to be updated. So looking to cavitation, as I said before, low-level outlets are not meant to be used constantly due to severe issues that they can face. And some of those are gate vibration, which are due to the high-speed flows, gate clogging due to debris, which can be sediments or wood debris, but also hydroabrasion and cavitation. And in particular, if you focus here, this is a picture of a cavitating bubble. So when the pressure of the air inside this bubble drops below the vapor pressure, this bubble collapses in a very short time period, and a shock wave forms. And so the shock wave acts in a very small surface area, and therefore it exerts a very high impulse, very high force in a very limited area. And with ongoing operational time, this can create damages. And here, these are two pictures taken from the dam hydraulics book from IAHR et al. And you can see cavitation damages in Glen Canyon Dam and in a tunnel in Pakistan. And you can see that rebars are completely exposed here and here. So just to give you an idea of how dangerous cavitation can be. So going to my PhD project, as I introduced before, most low-level outlets are very old, and we are facing climate change, which will increase the demand. And here in this picture, you can see dam heightening works in Uzzone Dam in Ticino in 1998. So due to the sedimentation, reservoirs are losing a lot of capacity, so we need to perform dam heightening for hydropower purposes, but also for retaining the amount of water needed. And therefore, the knowledge of high-speed air water flows is crucial for safely design such structures. And the overarching goal of my project is therefore to develop a physically based method to predict the evolution of such flows. And to do so, I will use a large-scale physical model and novel analysis and novel analysis techniques and instrumentation. So just to give you an overview of the setup. So this is the low-level outlet physical model that we have at ETH. So here we have the pressurized inflow, which is consists of a pipe which is directly connected to our high-head pumps. Here you have the gate chamber. So from the other side, the view is similar to this. And we have an air vent to provide aeration to the flow, to the gate chamber, and then the free surface tunnel flow to discharge the free surface flow to the atmosphere. And some videos of the operation of this large-scale model. So we have hydraulic heads at the gate up to 30 meters of water column. Discharge is up to 700 meters per second. And the tunnel is 20 centimeters wide and 30 centimeters high and 20 meters long. And compared to dams in Switzerland, it scales 1 to 5, 1 to 20. So first thing to care about when doing hydraulic engineering modeling is scale effect. So here I would like to present a picture taken from the paper from Valentin Heller, from Professor Heller. And this is, I think it's like the Bible for hydraulic modelers. So probably you already know about that. But here you can see a physical model on the left, which is geometrically scaled to a scale 1 to 30 with respect to the prototype. And you can see that the flow variation is very different in the two. This is because it has been scaled with fruit similarity, but the Weber number doesn't match. And therefore, the air entrainment cannot be well modeled. And talking about similarity, there are 3 different types. So the easiest one to achieve is the geometric one, so similarity in shape. Then if we add similarity of motion, we reach the kinematic similarity. And then if we also manage to keep identical force ratios between model and prototype, we achieve the dynamic similarity. The bad news is that dynamic similarity can be achieved only for a scale 1 to 1 if water is used. Because of course we could also use another fluid, we could add some soap to water to decrease its viscosity, but it's not recommended for high-speed flows. And in case of my model, we scaled with fruit similarities, so we are trying to match the fruit number between model and prototype, and this is good for highly turbulent phenomena because the energy dissipation mainly depends on the turbulent shear stress. However, all the remaining force ratios, so all of this cannot be properly scaled. Is this a problem? It could be, but this could be a problem because scale effects could not be negligible. And here you have another example of a good geometrical scale, but as you can see, also the air entrainment is different. And again, here applause from Dr. Hormuth, my supervisor. And as you can see, these are all predicting equation of air demand versus fruit number in model and prototypes. And you can see there is a factor of scale of 10 at the power of 2, so huge scale effects. So the instrumentation I'm using, so electrical probes are broadly used for investigating high air water flows. And on the right, you can see an investigation that I performed last year to validate one of these conductivity probes against a high-speed camera. And from this, we can, from the signal of the leading and trailing tip, by cross-correlating these 2 signals. So in black, there are the signals from the leading tip, this one. In red, the ones from the trailing tip. And by cross-correlating these 2 signals, we can assess important flow properties such as void fraction, velocities, and also shear velocities. And just to let you understand better how such probes work, so as you can see, when the bubble touches the leading tip, the signal relative to the leading tip drops, while the one on the trailing tip stays up, and same for the trailing tip. So this is basically the signal of a complete interaction between the dual tip probe and the bubble. And just to wrap things up, because we are going a bit late, I would like to present you the investigation that I'm carrying on. So I'm carrying on air demand investigations where I'm using pressure sensors along the tunnel and also anemometers here in the air vent to get air velocities and then infer air discharges. And I'm performing probe tests to get air water flow properties. And in particular, I'm investigating the effect on air demand and flow properties of different tunnel roughnesses. So I'm lining the tunnel with roughness plates. At the moment, we have got 2, in order to model smooth concrete, abraded concrete, and blasted rock. And here there are some videos. So this is the gate chamber. You can see the roughness plates, the roughness plate just on the bottom. And here you have a closer look of such roughness plates. And upcoming investigations will include tunnel profile transition. So what are the effects of a larger tunnel and also linear or abrupt transition between the gate chamber and the tunnel? And also the effect of aerators, which is something that we see really often in spillways, but in low-level outlets, the literature is much more fragmented. So we would like to insert air vents also at the sides of this abrupt transition and at the bottom, in order to provide more air and see how our flow properties and air demand change. So this is all. I would like to thank you, and there is some time for questions, I think.
Thank you, Simone. Thank you for your presentation. So now that the discussion is open, we want to ask questions, comments. I can start with the questions. And yes, these water flows contains a lot of energy. So my question will be if it would be possible to exploit this energy, for example, with hydrokinetic turbines.
Yeah, very good question. Thanks, Emanuele. Yes, potentially. I mean, there is lot of energy, high energy flows, so fast flows. So we reach velocities up to 60 meters per second in prototypes. So ideally, yes. There are only two criticalities that come to my mind. First one is that low-level outlets are safety structures. So I mean, we don't want to occlude them in any ways. And the second one is about sediments, because the flow the sediment load in such flows can be very high, and probably this may represent a limitation, because such turbines could be damaged very soon. And so, but apart from these two criticalities, yeah, I mean, the potential, let's say that there is potential for such applications.
Yes, or maybe wind turbines close to the jet, not inside the jet, but because I suppose that also the air will be quite
exactly.
fast near the jet.
Yeah, exactly. There is a very strong
wind, yeah.
Very strong airflow, which can be in the same direction of the airflow, but we found out that it can also be counter current airflow, so it can also go in the opposite direction with respect to the flow, depending on the loss coefficient of the air vent. Yeah.
For example, a few months ago, I read a paper where the authors investigated the use of wind turbines to exploit the wind generated by cars in motorways.
Okay.
It could be a similar idea.
Yeah, exactly. I agree.
It could be a similar idea.
Totally agree.
There is a question in the chat. Are you going to use optical flow, PIV or BIV, to track the air bubbles in the flow?
Yeah, thanks for the question. Very good question. And unfortunately, all kind of optical methods cannot be used in such flows due to the very high aeration. So you could actually use them to the very close to the wall. So in my model, we have acrylic glass walls. So probably to investigate the flow attached to the wall, yes, you could potentially use them, but you cannot at all penetrate with PIV to the core of the flow because of the high turbulence levels and aeration. So just to go back to typical flow conditions. So this is the kind of flow we are talking about. So it's almost impossible to use PIV or optical flow with these flow conditions. And also that has been successfully used for spillways, for examples, but because you have access from the top. So of course, spillways are not closed conduits, and you could use optical flow and also BIV to assess the aeration of the flow over spillways. But for low-level outlets, we already tried. My supervisor already tried. It's basically almost impossible, except close to the wall, of course. But there are some effects due to the wall, so there is wall influence. So I wouldn't do that actually.
Okay, there is another question. Do you have results on the sightseeing of aerators?
No, actually, no. It's something we are planning, that we are building right now, but at the moment, no results on that. Will be the very last part of my PhD. So yeah, I mean, if you keep updated on my project, there will be several publications. So in a couple of years, hopefully there will be something about aerators in low-level outlets.
Good. Are there other comments or questions?
Yes, I have a question, Simone.
Yeah.
I'm still a bit concerned, but about the scale effects of your project, because I mean one of the main things that drive variation is clearly well, I mean, on one side you have the Weber number on the lower limit. And then on the upper limit, you have the energy over which a bubble of a determined size penetrates the free surface. In your scale models, I imagine you will be working on the very high end of the spectrum, meaning that since you are forcing with the blade, or not the blade, with the gate, you are forcing the entrainment of air. Then you are working on the very high turbulent regime of air entrainment. Now, since you are forcing the air boundary layer to go towards the wall, I wonder if you are also modulating a bit or not. I mean, you are modulating the stress as well on the wall. How do you call it? Yeah, on the wall below, which would, in the end, affect also the production of, or not the production, the cavitation, because you are inducing air in the system with very big bubbles relative to the size of the height of the channel. Are you there, Simone?
Yeah. I'm here. Yeah. I couldn't hear.
My signal is very bad. So.
Yeah.
Anyway,
I can hear.
So my point is, the size of your bubbles are very big.
Yeah, I agree.
Size of the channel.
So, yeah, I agree.
What does it mean that for cavitation? Because usually cavitation in a big channel, we're speaking of bubbles of millimeters.
Yeah.
But then you have bubbles of in the width of the channel, they scale. Yeah, they are 1 over 1,000.
I mean, I mean, I completely agree with what you're saying, but I mean, I think that's actually a limitation of physical modeling that we cannot overcome. I mean, it will be, I mean, always that your bubble in your physical models will be about of the same size of the prototype, and so they will be not geometrically scaled. So except of, let's say, changing the fluid, which is not something that we can do, of course. But I mean, I see it as one of the limitations of the main limitations. And the only thing that we can do to limit that is like to increase our Reynolds numbers in a way that we are in a very turbulent regime, so trying to match the Reynolds number of the prototype in order to have the viscous effect to be as small as possible. But actually, except of, as I said, changing the viscosity of the fluid, which is not something that at the moment we can do with such with such fast flows. I mean, I see it as an intrinsic limitation of physical modeling, and I don't see any way to completely overcome that.
And do you guys plan to do studies on cavitation without surface area, without bulking?
Without, sorry,
without bulking.
No, actually, no. I mean, we won't focus too much on cavitation. I mean, we will focus on cavitation, but the point will more be the effect that let's say our tunnel roughness, profile transitions, and aerators will have on the flow aeration, because it has been proved by many studies that you just need of a 5%, 4%, 6% of air close to the tunnel invert to completely avoid cavitation or to limit it a lot. So that would be the main focus to study the aeration in the layer of flow very close to the invert.
Because in the beginning perhaps I understood incorrectly. I thought the objective was to study cavitation itself. But
no, actually no. It's an issue of low-level outlets. So in a way, I'm trying to design low-level outlets in a safe way. So cavitation, of course, is involved, but it won't be like a study focused on cavitation, but more on different geometrical parameters and features of low-level outlets, and how they affect cavitation.
How they affect cavitation, but basically, so the study is more over radiation itself.
Exactly.
Okay.
But that's of course a very interesting, let's say, side project.
I'll be interested in any case to see your the air fraction profiles, if you can extract them.
Sure.
Be definitely following your work.
Yeah. Thank you very much.
Yeah.
Okay, thank you. There is another question in the chat for Simone. Do you plan to represent historic cases of cavitation incidents on dams?
Actually, that I mean, I haven't done it yet, but it's quite well. You can find in literature many studies. I'm thinking about Falvey in 1990, who published nice pictures and also cases of failure of hydraulic structures due to cavitation. And yeah, probably it would be good to have a chapter in my thesis where I summarize, let's say, historic cases of cavitations, but I mean at the moment nothing is planned. But again, if you check in literature, I mean if you email me, I've got some good papers who already did that.
Okay. Thank you. In the chat there are not other questions. So if there are not other questions or any comment, we could stop here.
Yeah, I would
Simone,
just,
we want to say something.
I would just to make a bit of publicity. So next coffee break in 2 weeks by our president Melissa about remote sensing for defining biomass features in a morphodynamic models. And so save the date and we will publish the announcement on LinkedIn and Twitter. So yeah.
Okay. So are there any other comments? Yes, the presentation will be available because we record them and upload them on YouTube. We will post our presentations also in post on LinkedIn, so you will be able to see them again. Okay, so we can close here. Thank you very much, Simone. Thank you also to all the other attendees, and hope to see you again in other webinars.
Thank you.
Thank you very much.
Thank you. Bye-bye.
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 Thank you.
Bye-bye.